Good afternoon. Thank you very much for having me here. I'm trying not to use mic. Is it okay with you? Do you hear me? Okay, good. So as you see, here is Albert Einstein on a bike. Albert Einstein was an eager cyclist. And as a cyclist, he appreciated very much the grasp of the present, of the now. Well, it's essential to correct grasp the present. Well, things could go completely awry if we mistake what is now. Also, being a cyclist, he appreciated the notion of real possibilities. The story has it that on that picture, he is negotiating with a cat. The cat is in front of him, and it's open whether he will overrun the cat, whether he will avoid it, or whether he will fall down. So at that very moment, there are these three real possibilities. Of course, they will disappear in a moment. They are very much dependent on that particular time, also on the location, and, well, on the concrete state of the world. If the bicycle had a somewhat different inclination, well, avoiding the cat wouldn't be possible. Well, the story has it that he avoided the cat. Well, so having that background of Einstein being both appreciative of the tenses, now, past, and the future, and real possibilities, it's no wonder what we read here from Carnap's memoirs. Once Einstein said that the problem of the now worried him seriously. He explained that the experience of the now means something special for man, something essentially different from the past and the future, but that this important difference does not and cannot occur within physics, that this experience cannot be grasped by science, seemed to him a matter of painful but inevitable resignation. So the subject of my talk is the notions like past, present, and future, as well as real possibility, actuality, possibility in general. As we see, there is this controversy whether physics has room for it or for them, and I will try to diagnose the situation. But let me contrapose Einstein's views with 3 or 4 other thinkers that were somehow dismissive of Einstein's worry. So here's the philosopher, Rudolf Carnap, continuing basically in his memoirs. So he says, that I remarked to Einstein that all that occurs objectively can be described in science. On the other hand, the temporal sequence of events is described in physics. And on the other hand, the peculiarities of man's experience with respect to time, including his different attitude toward past, present, and future, can be described and, in principle, explained in psychology. But Einstein thought that these scientific descriptions cannot possibly satisfy our human needs. I definitely had the impression that Einstein's thinking on this point involved a lack of distinction between experience and knowledge. To continue in this mode, here is the early statement of what is now known as the consciousness-based concept of becoming possibility and tense. And that's the quote from Hermann Weyl, who says, the objective world simply is. It does not happen. Only to the gaze of my consciousness, crawling along the lifeline of my body, does a section of this world come to life as a fleeting image in space, which continuously changes in time. Good piece of poetry, I think. And finally, a somewhat more recent statement of Rovelli: the notion of present, of the now, is completely absent from the description of the world in physical terms. Well, should we worry about there being no room for those notions in physics? And well, should we first diagnose what does it mean that these notions have no room in physics? So to begin with my two-legged diagnosis, the first leg is the observation that all these problematic notions are what philosophers call indexicals. So the notion of now, as well as the present, the past, the future, as well as the notion of actual as the actual outcome of some measurement, contraposed with possible outcomes of a given measurement. All these things are the so-called indexical notions. And what does it mean to say that some notion is indexical? Well, the concept comes to the fore once we consider questions like, what is the difference between the actual outcome and one's possible outcomes of a given experiment? So think of tossing a coin. Or what's the difference between my present talk and my yesterday's talk? Well, on the supposition that I did give a talk yesterday. And the answer here is two-legged. The first is that we can point to the former. So hence the name indexical. We can point, you can point or you can focus on my present talk. Okay? Similarly, you can point or focus on the actual outcome of a given experiment. So that's this pointing or focusing idea. And the second idea is the so-called democracy, namely, if things were different, namely in that particular experiment, a different outcome materialized, then I would point to that other thing. And similarly, if today were Wednesday, you could focus on my yesterday's talk and not on my present talk. So there is this concept of democracy. These two notions are the essence of indexicals. Well, indexicals are they were first studied in logic or philosophy of language, and here the important distinction is between the so-called eternal sentences that do not contain indexical words like I, she, now, the past, here, there, actual, really possible. So these are the eternal sentences. And these were contraposed to the so-called sentences with indexicals. The important observation here is that over the last 60 years or so, there has been quite a change of attitude to indexicals, or more precisely, attitude on the one hand to eternal sentences and on the other hand to the indexical sentences. So 100 years ago or so, Twardowski claimed that all these sentences with indexicals, like for instance, it's now raining in Lvov, that they are due to speakers' clumsiness and they are not really in realm of logic, which it means they are not bearers of true values, so only eternal sentences are good. And in that spirit, the Tarski's concept of truth was born, so truth was relativized to a model, just to a model. Well, but then, started from the late 60s, situations started changing quite dramatically. So first, there were arguments that took sway, finally, that language is essentially indexical, namely that there is some meaning in sentences with indexical elements, like, for instance, well, I'm getting out of a dentist and saying, well, thanks goodness it's over. you cannot translate the sentence with all that's meaning in eternal sentences. So there was that sort of argument to the effect that language is essentially indexical, and that had an impact on logic. So nowadays, there are more complex analysis of truth. So truth is analyzed in a model, like in old times of Tarski, but also at an evaluation point, and they are initialized by context. So that was quite a large difference. A similar development concerned epistemology, namely our thoughts. And by quite a similar sort of arguments, the view took sway that thoughts are essentially indexicals. Here are a few names of people that were involved in that campaign. So I take it as these two claims, that language is essentially indexicals and thoughts are essentially indexicals. I thought it as well-established claims. I teach them to second or first year students of philosophy, so no more word about it. However, I'm putting forward next thesis, which says reality is essentially indexical. That's not a popular view, but I'm proposing it, and well, we'll see what consequences that view has. What does it mean that reality is essentially indexical? So that view comprises three ideas, namely the idea of floating time in terms of a passage, past, present, future. So the distinction of tenses is objective. Second idea is the concept of passing possibilities. There are things that are possible now for me, but in a second they will be gone. Okay? So there's that concept of real possibilities that includes passing possibilities. And the third thesis is an epistemological, which says, well, we somehow developed some means to get acquainted with the indexical part of reality. And that's indexical elements in our language, as well as indexical elements in our thoughts. Of that ability of pointing to the present or pointing to the actual outcome of some experiment, well, they are not infallible. Could happen that I'm mistaken about what the present is, but well, here it is, this ability. I'm returning after this big introduction to physics to ask these two questions, namely, why there is no room for now, as well as the past and the present in physics, and similarly, why there is no room for the notion of actual or really possible in physics. Well, to develop on these two questions, well, there seems to be two problems. The first is, as I just explained in my introductions, that, well, these notions are indexicals, and, well, no language that's formed in terms of eternal sentences cannot capture these indexical of elements. And it so happened that a language of encyclopedia and a language of handbooks, is it physics or chemistry or biology handbooks, is the language of mathematics. They are all non-indexical language. There is no room for now or the actual in these languages. So, given the development in philosophy of language with the emphasis that, well, the indexical notions cannot be grasped, cannot be captured by languages with eternal sentences only, well, physics, since it operates with with languages formed in internal sentences, they cannot capture these terms, the terms like the now, present, future, actual, actual outcome versus possible outcome. Simply, there is no answer, if that theory is true, there is no answer in physics why, in that particular experiment, we've got this actual outcome and not some other outcome, which was a moment ago still possible. Okay? So that's the thesis, that we cannot grasp in physics actual versus merely possible or now versus past. But, well, that's the first part. But there's the second part, which sometimes in the literature is called the questions of locus. And it's easier to explain with respect to time. Namely, we could ask in our eternal sentence language, what is a region of now? So we are pointing, say, to a given point event, like my knocking at the table, and asking, well, what is the present of that particular event? What's the region of the present? And similarly, abstracting from grasping the real possibilities, we may ask, what is, mathematically speaking, alternative possibilities? What mathematical structures they have? And here physics seems to be extremely important, because it could provide, by studies of initial value problem, what these alternative possibilities, that is, alternative evolutions, are. All right, so the indexical part is over. Now I'm turning to discussing how physics search, or how it can search of loci for real possibilities, and whether it's biased or not in that search. So to begin with a little introduction, the question about this structure of alternative possibilities translate into, do some physical systems admit alternative evolutions? And typically it's handled by a given physical theory. The physical theory comes with basic equations, so it could be Newton's second law, or Schrödinger equation, or Einstein-Fields equation. All the things that I just named, these are differential equations of various types. And in the theory of differential equation, we face the so-called initial value problem, which is, do the basic equations taken together with appropriate data about the system have a solution? That's the first question. The second question goes, is then the solution defined for the whole range of parameters? Typically, the parameters is time. So it's the question whether the solution exists for the whole interval of time. And finally, is a solution to the basic equations unique for each value of an appropriate parameter? And of course, this last question, the uniqueness, that's extremely important for the question whether there are alternative possibilities, but also that second question with a looming distinction between local versus global existence of the evolution, it's also extremely important. Well, the initial value problem has various phases, and just to give you a flavor of it, I focus my attention on ordinary differential equations, where things are clear. That is, they are theorems that give the verdict. So as for the first question, namely about the existence, we have Peano theorem that assures the existence given the condition of continuity is satisfied. As for uniqueness, local uniqueness, we have Picard-Lindelof theorem that under condition of Lipschitz's condition gives positive verdict. There is a unique local solution. And the unique local solutions are extendable into global solution. The verdict is yes. The condition is continuity. So generally, by looking at the big perspective of all differential equations, there are two sources of global non-unique solutions. Either we have local non-uniqueness, or we can have local uniqueness, but this local unique solution is not extendable to the entire range of time parameters. That's about ordinary differential equations. But of course, physics utilizes many other differential equations. And these different kinds of differential equations have different theorems, different conditions for securing uniqueness and extendability. These conditions are much stricter than in the ordinary differential case. And, well, often they are not proven yet. So it's not known what the situation is like. However, the main message of that of the studies of initial value problem in differential equation is pessimistic. That is, non-unique or non-extendable solutions abound in mathematics. Okay. Now, this rather gloomy vision changes once we move from mathematics to physics. You can open one or another book on differential equations for physicists, and you could read the following optimistic claim. If a differential equation adequately represents the physical process, then one expects it to have a unique solution. That's from a Richard handbook. So one may wonder, what happens here? Is there some secret understanding between the physicist and the creator? That is, in mathematics, there is this abundance of equations with non-unique solutions. We come to physical application, and boom, well, the optimism is around us. So the question is, whence this optimism? Well, the optimism is not a mystery. It rather follows from some guidelines how to construct physical theories. And the person who thought quite a bit about the subject and also is very influential in physics is the Princeton-based mathematician and physicist Hadamard. More than 100 years ago, he reflected what does it mean to have a mathematical model of physical phenomena. And here is the statement. A mathematical model of physical phenomena or a problem that the model contains is to be well posed. And then he continued to explain, the problem is well posed if it has a solution, the solution is unique, and the solution's behavior changes continuously with the initial data and parameters. That's informal, so you could understand the claims in somewhat different manners depending on how you understand the initial data or changing continuously, but basically that's the idea of well-posedness. The idea is still well and kicking. So just to substantiate that it's still alive, here is a statement from Rob Wall's handbook on general relativity, from a paragraph where he discusses whether general relativity deserves to be called a theory of physics. And he begins first by saying that the GRW, GR can be given appropriate initial data formulation such that the subsequent dynamical evolution of the system is uniquely determined. And then he continues by mentioning the small changes in the data, small changes in the solution thing. And finally, he gives a justification for that Hadamardyan vision by saying that only such a theory is manageable, can be tested in experiments. All right, well, we know the guidelines for theory construction, but of course, that does not assure that the world would comply with the guidelines. So the question is, what one should do if the phenomena are reluctant to be to comply with the guidelines. Well, what I think is at work here are strategies that guard physics against assuming or against accepting alternative possible evolutions. There are those four strategies which I will illustrate through the end of my talk. So the background of these strategies is the following situation. Well, somehow by solving the basic equation of a given theory, we come across a number of solutions for the same initial data. What should we do? So the first strategy says, well, the object under consideration is not a system of our theory, so dismiss it. It's not our theory's business. The second option, also used in the field, is to say, well, we've got these multiple solutions, but as a matter of fact, it's only one solution. Physically, they mean one and the same thing. The third option is to say, well, we've got so many solutions, but with exception of a given one, all the others are not physical. And finally, there is this sheer optimistic move, which says, well, it happens that our theory has multiple solutions. That's because our theory is not good enough. It's not adequate enough. If we add some more realistic terms, the resulting theory will surely be deterministic. So here are these four strategies that guard physics against accepting real possibilities, and here are the illustration. So that's the illustration for the first approach, which says the object is not a system of our theory, and that's the famous Norton dome example published a few years ago that provides a counterexample to determinism of classical mechanics. So here is a dome with a particular inclination of that surface. So this inclination is coded here, excuse me, in this formula. H is the vertical coordinate, R is the radial coordinate calculated on the dome's subject, and the mass point is on the top. It's stationary. The force is the uniform gravitational force. So by solving Newton's equations and adding the initial value problem, we are about to solve these two equations. And voila, we've got plenty of solutions. So we've got the R infinity solution, which is just the stationary solution, meaning, well, the mass would remain forever on the top. And then there is an infinite class of solutions which say, well, up to the time b, the mass remains on the top, but then after time b, it starts moving down the dome. And there are infinitely many such solutions. Well, the initial data are the same, so definitely we have a problem with uniqueness here. Yeah. So how can we diagnose the situation? Well, one popular way is to go into D'Alembert formulation of classical mechanics and note that this formulation requires the satisfaction of these two equations, where the second equation here is the constraint equation, which is written here. And for the second line here to make sense, the constraint F must be, and here's the big question mark, namely, in some handbooks like Rubinovich, the answer is continuity 1, C1. In some other handbooks, that's C2. And that's the crucial question, because our constraint, which is just this one, is C1, but not C2. So, leaving aside the discussion, what's the meaning of this controversy, C1 or C2, for the constraint equation, for my purposes, we see here a dispute whether the object is a system of classical mechanics or not, just at that very point, namely whether we should impose the requirement of C1 or C2 for the constraint equation. And of course, if physicists convince themselves that they need C2, the object would be dismissed and would not count as an example of, as a counterexample to determinism of classical mechanics. Well, here is the second strategy, which says, well, we've got many solutions, but these solutions are physically the same, and that's theories with gauge freedom. The story of gauge freedom is that, well, it's a very effective method of constructing theories, but very frequently, as Ehrman here says, the history of physics shows that the primary reason for seeing gauge freedom at work is to maintain determinism. And here is a quote from Rovelli explaining Dirac's argument for non-gauge invariant observables that exemplifies that sort of motion at work. So we begin by recalling Dirac's argument against the possibility of measuring non-gauge invariant observables. Suppose the equations of motion of classical system do not uniquely determine the evolution, so that the same initial data can evolve either to a later set of data A or to a set B, always respecting the equation of motion. Then we say that A and B are gauge related. And now Dirac argues that in this situation, the only way determinism can be respected is to assume that only observables that have the same value on the set A and on the set B could be observed. Following Dirac, we call these observables gauge invariant observables. So the big question here, of course, is why we need, or physics need to assume that, or assure that determinism is a good option. Here's the third strategy, which says, well, we've got plenty of these solutions, but most of these solutions are not physical, and a typical locus where this strategy is used is general relativity, because Einstein field equations are liberal enough, so they allow for quite a number of solutions. And to make things worse, well, the initial value problem of general relativity has this ambiguous feature. Namely, if we concentrate on nice developments, that is four-dimensional GR spacetimes, we have a uniqueness result. So to say it in more detail, the initial value problem in general relativity is the following question. We are given a three-dimensional space with Riemannian metric and some data on the space, and the question now is, can it be uniquely extended to a four-dimensional spacetimes with Lorentzian metric, and that satisfies Einstein's equations. So if we focus on nice four-dimensional spacetimes, then nice meaning hyperbolic spacetimes, then we have a uniqueness result due to Choquet, Bruhat, and Garrosh, which says each set of appropriate initial data of general relativity has a unique extension as a maximally globally hyperbolic spacetime. Of course, this theorem doesn't say anything for a relaxed case if we allow the extension not to be so nice, that is, not to be globally hyperbolic. And there are constructions just exhibiting non-unique extensions of three-dimensional spacetimes in general relativity. But here, the ideology helps, namely the so-called strong censorship conjecture, and especially one interpretation of it. This censorship conjecture says that for generic initial data, the maximal globally hyperbolic development thereof is not extendable. And, well, here the tricky thing is to understand the notion of generic. But on the one interpretation, this censorship hypothesis says initial data for which its maximal globally hyperbolic development is further extendable are not physical. So that's how this strategy of the solution are not physical works here. We have a plethora of multiple solutions to Einstein's field equations. And, well, these solutions are not intuitively nice. Okay? There's no nicely defined intuitive time there. So on the strong censorship conjecture, given that interpretation, people are saying, well, there is this plethora of those solutions, but no worry. These solutions have no physical meaning. They do not represent physical spacetime. Okay. Finally, the last strategy, which is this optimistic strategy. We have a theory with multiple solutions given initial data, but we are saying, well, as the theory falls, the next, the better theory, would have unique solutions. And here is a theory, a case in point, namely the so-called inviscid Burger's equations, which, for instance, describe the formulation of shock waves. And it's mathematically, the solution is very interesting because, locally speaking, it has unique solutions. Okay? However, these unique solutions are not extendable. So you cannot glue together a number of unique solutions to produce a globally unique solutions. So the diagnosis, or a popular diagnosis of that equation, is that it involves indeterminism, that it has alternative evolutions. But, well, here is the crucial observation, namely, if we add a certain further term, which is called viscosity term, then the situation would dramatically improve. Namely, with the term added, global uniqueness is regained. Well, so in other words, the initial value problem for Burger's equation with viscosity term has unique solutions. It's more important, perhaps, to look at the comment of physicists describing the story. That's what they say. The solution of the inviscid Burger's equation becomes multivalued. The multivaluedness is, in general, physically inadmissible. The mathematical model is too idealized, and it may have neglected some essential mechanism relevant to the problem. We neglected the term associated with viscosity in that previous development. So far, so good. I mean, if we focus on that particular example, things ended up nicely. But I think generally the ideology is pretty suspectful. If we have, the ideology roughly says, if we have multiple solutions, that's the problem of inadequate theory, and that comes with the belief that the adequate theory would be deterministic, would have only one solution. I overviewed a few strategies that, as I understand, have a role of ensuring the satisfaction of Hadamar's guidelines for a theory construction. So one may wonder why the guidelines and the strategies that follow, why they are important for a practice of physics. And my claim is that all these strategies, including the guidelines, they come from epistemological concepts. Obviously, a deterministic explanation is better than non-deterministic explanation. Non-deterministic probabilistic explanation is still better than non-deterministic without probabilities. Second, a sure prediction is better than a probabilistic prediction. And finally, experimental testing requires stability. Bowing my head to all these epistemological concerns, as after all I'm a chair of the epistemology unit of JU, I still wonder, namely, what if in our world some possibilities are real? That is, some systems face alternative possible future evolutions. How can biased physics see them? That's my question, and I think it's a good time to stop my talk. Thank you very much.